Okay, hello everyone. Welcome to this week's Quant seminar. Today we have two talks. The first talk is given by Kyongmin Yeo. Dr. Yeo obtained his PhD actually from here, from Division of Applied Mathematics at Brown University at 2011. After that, he went to the Lawrence Berkeley National Lab as a postdoctoral fellow for 2 years before joining the IBM T.J. Watson Research Center. His current research interests include deep learning for time series problems, hybrid physics statistics modeling of spatial temporal process, and an atmospheric inverse problem. So without further ado, welcome back.
Okay, thank you for the introduction. So just for the time check, this is the one hour seminar, right?
Yeah.
Okay, great. So then let me share my screen.
Yeah, go ahead.
Okay, so then let's begin. So the topic I'm going to talk today is mostly about the good old-fashioned time series sequential inference problem. But the main focus is how can you make this sequential inference more flexible by using some techniques in deep neural network. This research is in collaboration with John Lee. She was an extern student last year from RPI, and my colleague Wes in IBM Research. So first, let me just talk about the problem setup that we want to look at. So here we are just looking at the same time sequential inference problem for time series, but we make an assumption that we have the data from some dynamical system. The actual form of the dynamical system is not really important, but we want to lay the foundation such that we are looking at a system which is invariant in time, so that we are not dealing with a non-stationary process. And we also have the discrete noise observation. So instead, we don't really observe the ground truth. What we have is the discrete sampling of the continuous time process with some additional white noise. Then the problem we usually interested in this sequential inference is twofold. Let's say we are given a noise observation of the sensor data. And then we are interested in two problems. One is that what's going to be the time evolving structure? Given the past trajectory of the data of the time t, what's going to be the probability distribution of the next time step? And once we can identify this time evolving structure, then we want to know that how the system will evolve in the future. So given the data of the time step t, we want to know the future state from t+1 to the prediction horizon t plus h. So this is a very standard problem setup for this time series inference. And this time series inference now becomes just in this time series problem. What we are interested in is to learn data generating distributions as shown here. Let's say this P is data generating distributions of the sequence 0 to T. Then we can, of course, use the product rule to convert this data generating distribution into the product of conditionals. So if we just look at this product of conditionals, then it's essentially having a fully connected graph structure. That the probability distribution at time step t has a connection all the way up to the initial state. So this is not really easy to make an inference. So the usual way people are doing, we are looking at it is that instead of having this fully connected graph structure, we want to use some state space model, which is summarized on the figure right. In this state space model, we assume that there is a hidden state or state space denoted by H. And given this H, now we make an assumption that the future state is independent from the past. So the fully connected graph structure shown on the left can be simplified to the product of two distributions as shown on the right. And in this case, we are making a conditional independence assumption that once the hidden state H is observed, now xt is independent from everything happened in the past. And recurrent neural network is essentially one of these hidden state, state space modules. So in recurrent neural network, we are computing the hidden state by some function, and this function is taking the hidden state of the previous time steps and the sensor data, or like a time series data, as an input. And then based on this hidden state, we are training another function G, which maps the hidden state to the time series we are trying to make the predictions. So the problem of recurrent neural network now goes down to how we can estimate these two functions f and g. So the usual way to train recurrent neural network for this time series problem is based on the maximum log likelihood method. So we can let's say this p is the likelihood function, and this p is a function of all the time steps x denoted by x, as well as all the hidden state denoted by capital H. And then since the hidden state is not really observable, what we have to do is that we need to marginalize this hidden state out so that we can get a log likelihood function for the sensor data X. And by using the conditional independence assumption, now we can simplify this log likelihood function into something like here. So we have the log of the product of emission probability. This emission probability is computing the sensor data or computing some dynamical system data given the hidden state and some of the prior. So then because we are looking at the log of a product, we can convert this product into the summations. Then here one question is that what's going to be the emission probability? So we usually use some kind of parametric assumptions for this emission probability. There are two major assumptions we are usually making for the time series inference problem. One is that when you have this when you want to estimate this emission probability, this X is a multivariate time series, so the dimension can be high. But since it's very difficult to estimate the joint distributions of xt, we usually make an assumption that this xt is independent in each of the dimensions. So instead of looking at the joint distribution, now we are looking at the product of each dimensions. And then we also make further simplifications such that each of these dimensions is parameterized by Gaussian distribution, so that each dimensions given by Gaussian distribution as shown here, and the mean and the standard deviation of this Gaussian distribution. So for each dimension is parameterized by the hidden state, and usually this function of the mean and standard deviations are given by recurrent neural net. Given by a feed-forward neural network. So if we use these two assumptions, then we can simplify this log likelihood function as shown below. And if we are not interested in the uncertainty, or if we make an assumption that the sigma, the standard deviation of the Gaussian is 1, then the loss function reduces to standard mean square error loss. So when you train a recurrent neural network for this sequential inference problem with mean square error, mean square loss, usually we are going through all of these steps by making the independence and the Gaussian assumptions. So, and there is another issues of this sequential inference problem. Let's say we trained the recurrent neural network with these Gaussian models to make the prediction of the next time step. Then the question is, how can you make the predictions of the future? We want to, let's say we want to know that the system state 2 hours from the now, or 1 day from the now, then how can you make the predictions? One of the standard ways people are making this forecasting of the system state is just based on the recurrent nature of the problem. Let's say this psi is a recurrent neural network. Then we use the last data point, xt, to make the prediction of xt plus 1. And then now we use this xt plus 1 as an input and make the prediction of the next time step and going forward in a deterministic way. But because of the probabilistic nature of the recurrent neural network, as I explained in the previous slide, what we are estimating by the output of a recurrent neural network for this stochastic process or sequential inference problem is actually an expectation. So if we do this kind of naive forecasting method, what we are implicitly assuming is that what we are assuming is the expectation applied on the operator that's operated in recurrent neural network is equal to the operator applied on the expectation of the input variable. So this relation is true only when we have the linear function, such as Kalman filters. But when you have nonlinear models like the recurrent neural network, we can no longer make this kind of assumptions. So when you want to make this n-step ahead forecasting of the system state, we have to estimate the joint distribution of the future state, and we need to marginalize out all of the intermediate state. So in other words, when you want to make a prediction of the future state using recurrent neural network, we essentially need a Monte Carlo simulations so that we can have a sample from the distributions we are making inference. So there are two major issues why I'm reviewing all of these very basics of recurrent neural network for the time series problems. There are two because these are two major issues. So when you make an inference of this problem, there are two very limiting factors. One is that we usually need an assumption on the emission probability. We use parametric models, mostly Gaussian. And usually we only have an estimate of each of the dimensions, not the full joint distribution of the multivariate time series data. And another issue is in the forecasting. If we want to make a forecast from recurrent neural network, then first, of course, we need to be able to learn joint distribution of the future state. And once we learn the joint distribution, we also should be able to sample from this complex high-dimensional distribution efficiently to make the Monte Carlo simulations. So the main focus of this research is that why don't we use a generative adversarial network to relax some of the limitations of the past recurrent neural network. Here, let me just briefly review the generative adversarial network. Generative adversarial network was proposed in 2014, and it has become one of the most popular methods nowadays. In GAN, we train two neural network. One is the discriminator denoted by D here, and another is a generator. So the role of the generator is to take a random variable as an input and make a synthetic data X denoted by X star. And the role of the discriminator is to identify whether the input variable is coming from the actual data or it's coming from this synthetic data. And at the end of the day, one example shown here is that when random variable sampled from Gaussian is going in as an input to generator, it generates a human faces or it makes some very funny images or whatever. Then the question now we have is how does it really working for the real valued functions that we are interested in? So in generative adversarial network, the training is done by a minimax optimization of some cost function, and the cost function is shown here. So in this cost function, we have two terms. The first term is an expectation over the data, and the second term is an expectation over the random variable that's going to be an input to generator. And then we are trying to based on the training, the first term is coming from the true samples, that's the real data, and the second term is coming from the fake samples, that is something generated by a neural network. And the objective of this minimax training is that the discriminator tries to identify if the input is coming from the real data or coming from the fake samples, while the generator tries to make the fake sample as real as possible so that the discriminator cannot distinguish. So this notion of the true and fake samples makes perfect sense if you are thinking about the image analysis, because clearly, human face can be distinguished from the cat face or some weird images. But then what does it actually mean if we think about it in terms of the real numbers? Let's say we are just thinking about this x as a real number and what is fake and real. So this simple description doesn't really help to understand the behavior of GAN. So to understand the behavior of GAN for this real valued function, I just make some simple simplification of the problem. Let's say we have the data, and we can identify. Since we have the data, we can always identify the minimum and maximum range of the data, which is denoted by alpha 1 and alpha k. And we just make the say discretization. Let's say we can define a grid by a set of real numbers, and we can also define a associated partition. The partition simply means the bin of each grid. And then of course, we here make an assumption that each partition have the same width. Then based on these constructions, now we can define a empirical data generating distribution. So this empirical data generating distribution gives us a discrete probability distribution, which is shown on the bottom here. And this empirical data generating distribution simply saying that we count the number of data falling into one of these bins and divide it by the total number. And of course, if we have the infinite number of data, and if we reduce the size of the bin, then eventually what we can see is that this discrete probability is going to the probability density functions of the data generating distribution. But in reality, we don't really have the data generating distribution. We only have the data. So that's why we are starting to looking at this empirical data distributions in a discrete space. And in a similar way, now we can define a generator distribution. We still doing the bin counting. We generate a lot of data from these generators, and we count how many generated samples in each of the bin and divide it by the total number of the generated samples. Then it will give us the generator distribution, which is denoted by Qi in this case. So based on this simple simplification, now what we can show is that the minimax problem is now converted into the minimax problem over the partitions I, and then we maximize, and the minimax problem also becomes the minimization over the generator distribution and maximization over the discriminator. So the change here is that in the original formulation, what we are looking at the expectation over some random variable g, but now we are not really interested in the expectation over random variable g. Instead, what we are looking at is the expectation over only the generated samples q. So
we have. Sorry.
Sure.
Can I ask a question?
Sure, go ahead, please.
Do you have a reference for the this GAN to generate real value random variable distribution, or you come up with this method yourself?
Yeah, you don't really have a reference because people are not really interested in the real value.
Right. I never read such papers. So it's your work, right?
Yes, right.
Okay, thank you.
Okay, so but in essence, but here this is a simplification to understand how the GAN works for the real values functions. So anyway, when we had this optimization problem, now let's look at this simplified optimization problem instead of the original optimization problem. And then the way we train this optimization problem is usually using stochastic gradient descent, and we are alternating between two different steps. This step means the discriminator step. In this step, we fix the generator and we train the discriminator. So for this formulation, in the discriminator step, we fix the QI, and then we solve the maximization problem. And in G step, that's the generator optimization step. Now we fix the discriminator and we try to optimize the formulation with respect to the generator distribution QI. So then how it works? If you look at the discriminator step, then we have the maximization of the loss function. And this is actually a well-defined problem such that we can find solutions that discriminator of ith bucket, ith bin is given by this relation here. So simply saying that discriminator value is a ratio between the generated samples and the number of actual data in each of the bin. So that's actually okay. But the question is how the generator step works. So if you look at the generator step, now generator step can be simplified equation shown here. So we are looking at the maximization of Q summed over the entire bucket by this relation. And the issue here is that if the discriminator inside of the domain has a global maximum, then the solution of this generator is very simple. This generator distribution will be a delta function at the location of the maximum D. But if this D doesn't have the global maximum, let's say it has several maxima with the same values, then Q is unidentifiable. Anything can be solutions. You cannot really identify unique solutions for this problem. So in other words, discriminator step is very well defined, but in the generator step, you either going to the delta function or you are not, the solution is not identifiable. But somehow, if you don't think about this alternating strategy, and if you're just looking at the equilibrium solutions, then you end up with one equilibrium solution that all of the DI is 1/2, and at this state, this generator distribution should be equal to the data distribution. So you have the equilibrium solutions, but as you see in these alternating stages, it's actually very, very difficult to achieve because this generator step is always going towards the maximum of the discriminator. And so there are actually difficulties training with GAN. GAN training is notoriously difficult that everyone, I believe most people know by now. And if you look at it in terms of the real valued functions, there are two major problems. One is the cost of dimensionality. As I shown in the previous slides, that GAN training really depends on the empirical data distribution. So if we have multi dimensions, then the number of data to fill the bucket to get accurate empirical data distribution increases exponentially. So you can not really have that many data as the dimension of the problem increases. And another, and so like at high dimensions, you have to rely on some kind of the smoothness of artificial neural network. but you don't really have control over the smoothness of your neural network. And another issue that I didn't mention so far is the support of the generator, meaning that all of the analysis shown here is based on the assumption that the range of the data is equal to the range of the generated samples. Let's say this SP is the range of the data we have, and SQ is the range of the generated samples. So in all cases, we assume that these two are the same. But the question is, what if they are not the same? So there are two scenarios we can think about. One is that the range of the data is smaller than the range of the generated samples that is shown in the item 1. In this case, the optimization problem can be broken into two parts. One is the area. One is this area where we have both data and generated samples. In this slide, the red line is the support of the generated samples, and black line is the support of the data. So when you have these two mismatch, then in the first scenario, we have the same optimization problem in the range of the data. And where we don't have the data, we are solving the problem shown on the right. But in this case, it's straightforward because we don't have the data. Discriminator values in this area will go to 0. And eventually it will make this generator distribution in this area going to 0. So eventually the generator support of the generator shrinks to match the support of the data. But the problem is the other case. Let's look at the case where the support of the data is bigger than the support of the generator that's shown on the bottom. In this case, the black line, that's the support of data, is bigger than the support of the generated samples. And in the common range, of course, we have the same optimization problem that can be addressed. But in the area where we don't have generated samples, now in this optimization problem, the generator distribution does not appear in this optimization problem in this term on the right. So what it means is that generator doesn't really have any information on this black line, and it cannot really be optimized for this black line. It can only look at what's happening inside of its own support. And then generator inside of support, generator doesn't, when it's looking at its own support, generator doesn't really care about the absolute value of discriminator. So it doesn't really care whether discriminator value is 0.9 or 0.1. It only cares of the relative magnitude of the discriminator values inside of each range. So when this kind of situation happens, now the optimization problem doesn't really converge because the generator does not know that it should extend its range. It tries to optimize only inside of its own range, and then it may zoom in to one of the area where you have the local maxima of the discriminator. So because of these issues, when this second scenario happens, you will definitely have the mode collapsing type of problem. So because of these issues, the training GAN is very tricky, particularly for the real number values. Okay, so that's the review of the GAN. Now I'm going to talk about then how we want to use GAN for the time series problems and how we can mitigate some of the issues I just described. So the goal of our study is that we want to have the deep learning model to learn the time evolution of some of the data, some of the time series data, so that we want to learn these conditional distributions of the future state given the data. And we do like to have two neural networks simultaneously. One is a recurrent neural network, to actually capture the transition of the system state. So we want to learn the dynamics by using recurrent neural network. And on top of recurrent neural network, we want to have a generative adversarial network to learn the probability distributions. So the reason is, again, as I mentioned in the beginning, in most of the current recurrent neural network, we are limited. The capability of recurrent neural network is limited by a parametric assumption of the distribution. And here we want to relax the parametric assumptions of the recurrent neural network. So the idea, so the architecture we are looking at is something like this. So here we have the recurrent neural network that's taking a time series data as an input. And somehow we are expecting that this recurrent neural network has some implicit computation of the conditional distribution we want to estimate, which may be coming from GAN. Then we are using a random variable GT as an input to these distributions that will give us one sample, xt plus one star, by using from this conditional distribution. Then how can we train this recurrent neural network with GAN for the time series data? One of the conventional ways of training time series model is literally from the definition of GAN, definition of the original GAN. So people usually take the sequence of true data as shown in this slide, and also they generate the sequence of the samples, and then they put each sequence to the discriminator and try to solve this minimax problem. Sorry, there's a typo. Try to solve this minimax problem. So it's a straightforward extension of the original GAN formulation. But what they are actually trying to do by using original formulation is that the discriminator should be able to evaluate the ratio between the full jointed distribution of the time steps. So you can theoretically show that if you solve the optimization problem, then DI try to learn the ratio between, so here PG is the distribution, generator distribution that is Q shown in the previous simplified analysis, and PD means the data generating distribution. So they, in this way, they try to learn the ratio between these two. But as I explained in the previous slide, that comparing joint distribution is very, very, very difficult because of the high dimensionality. Let's say the dimension of X is like a 5-dimensional, and we have the sequence length of T, then we are looking at the 500-dimensional problem that you never be able to fill the data into this 5-dimensional space, 500-dimensional space. So what we are proposing is that instead of using the original formulations, now we slightly modify this the formulation as shown here. It simply means that now we are taking the expectation of x0 to t-1 from the data distribution. It is simply saying that we are using the data, moving the recurrent neural network up to time step t-1. And at t-1, now we are evaluating this loss function. And it's again simply saying that at t-1, we have the discriminator that's taking real samples, or that's taking a generated samples, and then try to identify whether it's coming from the data or not. So this formulation, again, from hereafter, all of the formulation I'm showing is mostly based on the expectation of the data, the generated distribution, not the latent, not the distribution of the input variables, because this is more straightforward analysis. It provides analysis more straightforward. So here, what we are proposing is that instead of comparing sequence to sequence, now we use the data and we are comparing only the next variable, only the next step in this objective function. So by changing the GAN loss function into this form, now we can say that the role of the discriminator now changes to evaluating the conditional distributions, not the full joint distributions. So the neural network architecture we are looking at has are like this. So the top row shows the generator. The generator consists of the recurrent neural network denoted by the psi that takes in the time series data as an input. And then we have the feed-forward neural network denoted by FG. And this feed-forward neural network takes the hidden state as an input, as well as some random variable. And then this FG is essentially GAN that's generating the samples. And for the discriminator, it has a similar structure that in this discriminator has a recurrent neural network that takes the time series data. And then we have a feed-forward neural network that takes in a sample data for denoted by X tilde, and it gives us a score where X tilde is from the generator or from the data. So that's the loss function we want to use to train neural network, but it didn't really solve the question we had about GAN difficulties of training GAN, such as the cost of dimensionality and the change of the support. And one of the issues of this change of support problem is because of the generator steps. As I mentioned before, the generator step is not really well defined. So here our proposal is that now we want to have a regularization on the generator step, such that we can mitigate some of the issues we saw before. First conditions we are thinking about the generator regularization is based on the consistent condition. The consistent condition means that in time series or in sequential inference problem, we know that the marginalization of the conditional distribution should be equal to the marginal distribution, which is shown here. So what we are trying to do is that, let's say we have this, again, this PG is the distribution of the generator. What we want to do is that we have discriminator distribution marginalized over x0 to t from the data distribution. And then what we would like to enforce is that this integral constraint, this integration or marginalization of the generator distribution is equal to the marginal distribution of the data. But we don't actually have the analytical formulation for the generator distribution. We only are able to sample from this distribution. Also, we don't actually have an analytical form of the data distribution, so we cannot evaluate we cannot evaluate this equality directly. So we propose to use a two-sample test based on MMD, maximum mean discrepancy measure, and then we have this using this MMD to identify to look at the difference between the left-hand side and right-hand side. Now we have the new loss function for the time series GAN we are looking at. The first one is again the formulation that we want to enforce the discriminator to learn the conditional distributions. And in the second formulation, now we are using MMD for the two samples. One is from the data and another is from the generators. So this is the first conditions what we want to impose for the consistency to regularize the consistency of the generated samples. And second condition is actually coming from the nature of the forecast. In the forecast problem, what we want to do is that we want to be able to sample from this joint distribution of the future. And since we cannot really estimate the joint distribution, we usually use a product rule, so that we break down this joint distribution into the product of conditionals and sample from each of the conditionals successively, like a sequential Monte Carlo method. So problem here is that if we do this successive sampling, and if we have an error in the estimation of each of these conditional probability distributions, then eventually the error accumulates. And at the end of the day, the solutions, okay, the samples the distribution we are trying to predict will diverge from the ground truth distribution. So the second consistency condition is actually coming from this realization that there is an accumulation error in terms of the multiple step OID forecast. So what we want to impose in this second consistency condition is, again, we want to have the marginalization of the data generating distribution, and we want to make this integrated marginalized data generating distribution is equal to the data generating distribution. But the problem here is that in the previous case of the first consistent conditions, we are comparing the marginal to another marginal. But in the second consistent condition, now we have to compare one conditional to another conditional. But we don't really, based on like based on the sample testing, but we don't really have a good method that can do the sample, that can compute the divergence between these two distributions when they are conditionals. So regularizing this conditional distribution becomes a very difficult problem. So instead of directly regularizing, imposing this condition on the conditional distributions, now we define another another random variable, that's the temporal difference. So n to the temporal difference denoted here is simply the xt plus n minus xt. And then what we are trying to regularize is that this temporal difference of generated distribution of this temporal difference versus the data distribution for this temporal difference. So we again converting this high dimensional problem into low dimensional problem, just comparing the marginals by changing the variable to the temporal difference. And there are two possible regularization strategies to comparing these two. One is again based on the MMD, so that we can look at the samples on the left-hand side and right-hand side and looking at using the same MMD. But another way we can think about is that we can use another GAN formulation to have to compare PG, to compare this temporal difference distributions of generator and the data. So based on these consistency regularizations, now we come up with three different formula, three different training methods. In the first training method, this is like a first order method that we are only imposing the first consistent condition, that we have the standard loss function plus the MMD loss. And we have the second consistent condition. We have second model shown here. That's now we on top of this first regularizations. Now we add the second consistent condition by using MMD, and we can have another method. In this method, now we are adding the second regularizations as another GAN formulation. So in the last model, we only have one generator that's generating the time series data based on the history, and then we have two discriminator. One discriminator is going into one discriminator is using looking at if the samples if the sample generated following the conditions that's inside of the loss function. And we have another discriminator that's trying to identify if generated samples will follow the marginal distribution over this temporal difference. So now in the last formulation, generator have to deal with two discriminators simultaneously. Now let's just see how the method actually works. Here I'm going to talk about three different numerical experiments with increasing complexity. The first one is autoregressive process, but we make the noise a little bit complicated by using Gaussian. In the second case, we are now looking at the chaotic time series, but we also add Gaussian noise. So the second case is more like we have the smooth ground truth and we have the noise added on top of it. And the last case is a random Lorentz system. This is a random Lorentz system is a Lorentz equation plus some white, some correlated white noise. So it's the last problem is stochastic differential equations, modeling the stochastic differential equations. So let's see how the model works. First, we look at the autoregressive process with Gaussian. The autoregressive process is shown here. This is simple autoregressive process, but we just make this epsilon t noise process to be Gaussian. If you look at the figure on the bottom, top left shows the distribution of this noise from the data. And we trained the neural network. The first case shown on the top right, labeled as B, is the estimated noise from the GAN. But in this case, we don't impose the consistency condition, so that you can see that the predicted distribution is very different from the ground truth distribution. And in this case, what you can see is that you can match, the generated sample actually matches the first and second moment, but it doesn't really match the exact form of the distributions. And in the bottom two case, now I'm showing you the generator distributions from the GAN. And we are looking at two different results by from two different regularization parameters. So in the first case, so here we are using MMD, maximum mean discrepancy measure, to regularize the behavior of generator. In this MMD, now we are using radial basis function denoted here as a corner, and this radial base function actually has one free parameter that is scale parameter gamma. So we change the gamma from 0.2 and 1.6, and when gamma is 0.2, the generator distribution is very similar to the ground truth. But when gamma is 1.6, the generator distribution still captures each bimodal, but the actual shape is a lot different from the data distribution. So we try to look at how the model behavior with respect to the changes in the regularization parameters. So to quantitatively show the results, we compute the KL divergence of these discrete samples. And if you look at the formulations of this GAN, there are two free parameters. One is lambda, that's essentially giving us the regularization strength, and another is gamma, that's the shape parameter of this radial basis function. In the first experiment shown on the bottom left, we fix lambda to some value, like 100 in this case, and we change gamma to see how the KL divergence changes. Then what you can see is that when gamma is small, when shape parameter is small, the KL divergence is very low, meaning that the error estimation is very low. And when gamma becomes larger, there is an increase in the KL divergence. And in the second case, now we fix the gamma. Now we fix it two different values, 0.2 and 1.6. Now we change the lambda. And when we fix the gamma, changing the lambda, now we have the error changes something like this. We have some optimal gamma values that give us the minimum KL divergence, but after that, it's just starting to increase. And this optimal lambda value is actually changing when you look at different gamma. So it's not really a convenient formulation because we have two parameters, lambda and gamma, and it looks like we have different optimal tuning parameters for this case. So instead of looking at this gamma and lambda independently, now we defined another parameter, another variable, which is shown as a loss ratio. This new variable is just a just the magnitude of regularization divided by the magnitude of the objective function. And what we found is that when you plot all of these KL divergence with respect to this new variable defined as a loss ratio, now we can have much uniform behavior that when this loss ratio is very small, meaning that when the regularization is very strong, then we have the very large KL divergence. But when this loss ratio is in the range of from 0.01 to 0.04, essentially it doesn't really matter how you choose individual lambda and gamma. As long as the combination makes the loss ratio in this range, the KL divergence can be stayed very low. So it provides some idea about how we can actually choose the gamma and penalty parameters gamma and lambda without doing extensive validations. In the next test case, now we are looking at the Mackey classification that's generated from this complex time series data, and the data looks like this. Here, the line is the ground truth, and the circles are the observations we are using to train neural network. And the noise is given by this very complex bimodal structure. And we have, and this figure just shows the, say, 500 forecast of the system state. In here, the red lines are the data, and we are starting the forecast from 0 to 500. And black line is the expectation of the expectation of the distribution, as well as 95% prediction interval. And in general, prediction is actually fairly good. And for the interest of time, I'm going to skip this part, but just going to the last part where we are looking at the stochastic system of random Lorentz equations. So the first part of random Lorentz equation is just a Lorentz equation, but now we are adding some white noise with covariance structure. Figure on the bottom showed what the trajectory looks like for this random Lorentz system. And clearly you can see that we are doing stochastic simulations. After time equal to 0, then there is bifurcations and all of these complex behaviors are happening. And this is just showing that the error measure comparing that. I'm not going to the details of what this error measure means, but what you can see is that the first number is coming from standard recurrent neural network with the Gaussian assumptions, and this number is coming from our model. That you can clearly see that our model is much more accurate than standard recurrent neural network. The reason is shown here. It means that let's say now we are looking at the three-dimensional system. We have X, Y, and G, and now we look at the joint distribution of the Lorentz system. In the first row, we are looking at the joint distribution in X and Y, and in the bottom row, we are looking at the distribution of X and G. And the left column is the data, and the rightmost column is the joint distribution estimated by our GAN. And in the middle, we have the recurrent neural network that's based on the Gaussian assumptions. And you can clearly see that joint estimation of joint distribution of recurrent neural network is not as good as is off from the actual data distribution, while our method provides a very good estimation of the data distribution. And so now we are looking at the effect of the second consistent condition. In this chart, what you can just think about this vertical axis as a kind of error measure. In the horizontal axis, we have the number of prediction steps. And what you can see is that this blue line is the prediction accuracy of this GAN with only first consistency condition. And this green line is a prediction with the second consistency condition. That you can clearly see that including second consistency condition in the training improves the accuracy a lot. So the summary of the talk today is that we are trying to import, we developed some GAN-based method to make a flexible estimation of the of joint distribution of time series. But training GAN is very tricky because of all the issues I described. So we proposed to regularize the behavior of the generator by imposing some consistent conditions based on the characteristics of the time series problem. And it's actually working well as we expected. So that for the interest of time, I'm going to stop here and please. Okay, so for the interest, I'm going to stop here. Thank you for your attention.
Thank you. I have a question. Could you like the
Sure.
general question? Could you go back to the slide where you define the loss function?
Sure.
You know, in the very early slides.
Oops.
Yeah, here. So, so for common GAN, we don't have access to the analytic expression of the data distribution, and we don't have the access to the generator distribution over the generator as well. So, that's why for regular GAN we use expectation to define the loss function, because we don't have the probability density function. So we sample from data and we sample from the generator. So my question is, so here you assume that in your loss function you use PD and PG, and they are PDF of the data. And
no. Yeah, but at the end of the day, it's estimated by the Monte Carlo estimation, right?
Oh.
And then PD is just sampling from the data. PG is just sampling from the generator. So it's going to be eventually going to the summation.
Yeah. So this integral is estimated by Monte Carlo estimation simulation, right?
Yeah.
Oh, okay.
Right. So it eventually just becomes the summation. It's like a standard again, but.
Okay. Like, what methods do you use to generate the MC chain?
Sorry.
Like, what method do you use? You use MCMC, right, or any other Monte Carlo method to generate?
It's like a SMC, but it's just like a standard Monte Carlo method that we are essentially we are essentially digesting real data up to X milestone as you train the recurrent neural network. And from here, you are generating the new data you are generating new samples by using a random variable as an input, and now evaluate the loss function in this step. And in the next step, you update the recurrent neural network again using the real data, and then repeating the same process again.
Yeah, and then on the bottom, the X tilde could be either the real data or the generated data, right?
Yeah. Each either real data or generated data.
Yeah, got it. Thank you. Do we have any more questions for our speaker from the audience? Okay, if we don't have any more questions, thank you, Dr. Yeo, for this presentation. It's a wonderful talk. Yeah, let's move on to the second talk. Our second talk is given by Simone Venturi and Tiernan. Simone is a postdoctoral appointee at Sandia National Laboratories, working at the extreme scale data science and analytics department under the mentorship of Dr. Tiernan. Simone's research mainly focuses on combining reduced order modeling and scientific machine learning for improving predictive capabilities in combustion and plasma chemistry applications. Before joining Sandia in March 2021, Simone was a graduate research assistant at the University of Illinois at Urbana-Champaign, working on hypersonics and non-equilibrium flows. So without further ado, let's welcome our second speaker. So Simone, you may want to start. Hi.
Yes, yeah, I need the sharing.
Oh, sorry, I'll make it.
That's okay.
Yeah, I think you can share now.
Let me try again. Still doesn't work. I have to.
Really? I think I just set you the co-host, so you're able to share the screen now.
let's see if it works now.
Still no?
No.
Let me try it again. Will you give it another try?
Yes, now it should work. Okay.
Oh, great.
You should be able to see it, right?
Okay. Yeah, of course.
Amazing. All right. Sorry for the inconvenience. Yeah, thank you so much for the introduction. So yeah, this is a work that we have done in collaboration with Tiernan here at Sandia National Labs. So it's very application oriented as the paper that's behind it. So I will give you an idea of the problems that we're working on. So one of the main projects is on turbulent combustion. I mean, you probably know that it's computationally expensive for many reasons, principally because of the resolution requirements, the scale with the cube of Reynolds number, and really all the scales need to be resolved in DNS, in direct numerical simulations, and the number of equations that need to be solved at the chemical level are become very huge. And you see here on the right what I mean. This is the evolution in terms of complexity in dimensionality of the mechanisms combustion in the last 20 years or so. In terms of number of species on the x-axis, number of reactions. So we really get at the level of tens of thousands of species and reactions. Problem when I was working on before joining Sandia was in hypersonics, and it's very similar in a certain sense. We have multi-physics, so you see here on the left in the picture how many different phenomena are involved simultaneously. What's really happening inside the shock layer is that the kinetic energy of the vehicle gets transformed into translational energy, but also internal energy. So the molecules start to rotate faster, to vibrate, and to get electronically excited as the atoms. So the mixture is actually thermally and chemically reactive. The real issue is that all of this happens in non-equilibrium. So you see here the straight lines that will correspond to the equilibrium distribution of the internal levels. And when we say internal levels, I really mean these rotational and vibrational states of the molecules of the order of tens of thousands as well. At equilibrium, that's supposed to be on straight lines. And what happens is that in the dynamics that we observe in the shock layer, they're actually not. So we really need the resolution at the molecular and atomic level in order to understand what's going on and to quantify the flow, the properties of the flow, and to design heat shields that are capable to resist those temperatures. So like the commonalities of these problems are really multi-scale and multidimensionality. So the lower scales of the physics, so that are governed by the chemistry, are important and fundamental, but also computational bottleneck. And the multidimensionality, again, is given by the number of states or the number of species that are involved. So the real goal of like some of the projects we're working on is accelerating chemical and thermal non-equilibrium chemistry predictions via reducer surrogates. So one approach that's been used in the past in the community, especially in the combustion community, is to first split the transport and the reaction dynamics and linearly project the reaction dynamics to reduce dimensional space. And normally, like linear encoder, like principal component analysis, for example, has been used widely. And then use simplified simulations, like 0D simulations, very simple chemistry, relatively simple chemistry, for generating the evolution of the states in the reduced space, and then map the source terms of these equations to the states, to the reduced states. This mapping is normally done with neural networks and like other type of machine learning surrogates, but the point is that these still requires integration. The OD still needs to be solved, even if in a reduced space and with surrogates. Now, this is an example of a real problem we were studying, and you see here that on the x-axis there are the number of dimensions. So the real problem contains 19 states, so 18 species and temperature. And we were reducing through PCA like incremental reductions. And you see that at the beginning, there is a real reduction in the number of right-hand side evaluations. But at a certain point, like it's not worth it anymore. Actually, gets worse, right? Because there is some additional stiffness other than the one already in the chemistry that's introduced in the integration by the surrogation, the short time surrogation. So what we really want to try here is something different, right? So trying to avoid the numerical integration. So in line with the neural operator approach, right? That's been so hot topic right now. So we are using deep operator networks, like assuming here everyone is familiar with. So starting from the Chen theorem 1995, and then the extension by Crunch group to DeepONet architecture. So what we are investigating in our paper and represent now is a different view on this DeepONet architecture that you guys proposed. That starts from the SVD analysis, right? In order to show what are like additional advantages of the training technique of the what I call vanilla DeepONet. So DeepONet in the original paper by Lulu and Kanidak's group. So I will present this with a very simple example. It's a linear system representing a mass spring damper physical system. So what you see on the left are the initial conditions that we sample, underneath the initial conditions in the displacements of the space and in the velocity. What we do, we forward propagate this initial condition through the simulation of the OD, and we obtain 100 scenarios, right, that we use for training. So these are on the left, on the right, red, all the red lines that you see in the next slides will be displacement, and the black lines will be velocity. So we want to construct an accurate emulator for this dynamics. Okay. So the way that we proceed is actually constructing a snapshot matrix. This is like slightly different from the classic snapshot matrix in POD, for example, because we have time on the like all these columns are different time instants of the same scenario. So different columns correspond to different scenarios, right? And what we do, we apply, we form SVD, like in the PCA form, right? So we obtain a matrix of principal components and a matrix of coefficients. So we do this, for example, for the displacement, but we also do that for velocity. So we obtain two matrix of coefficients and two matrix of principal components. And what we do is actually fitting the coefficients of this matrix here and the coefficients of this matrix here to two different blocks of neural networks. Okay, so these blocks for the coefficients will take the input of the ODE, so the initial conditions of the ODE, and we produce two of the modes, right? So two of the columns of the coefficients, and the same will be for the block for the principal components, which instead will have time as an input though. Okay, so we do something like this, right? So if we combine everything, yeah.
I'm sorry, can I interrupt a little bit?
Of course.
Yeah, could you go back to the previous slide?
Yes.
So actually you are learning A and phi, right?
That's exactly correct. Yes, we are mapping the coefficients as function of the initial condition. So, right, we can create an input matrix, which is given by the two columns, if you want, given by the initial conditions, right? And we already have performance with this. So we have the coefficients of this matrix here in form of two columns. So we're really creating mapping based on the data, output data and input data in a certain sense. And we do the same for the principal component.
Yeah, it says on this slide that you are mapped AX to X0, V0. So it's the other way around, right? You're learning a function from X0, V0 to AX. Yeah,
if you want, like, yes. So the coefficients are function of X0 and then V0 in the sense.
Oh, got it. Thank you.
Right. And this is like, I forgot to mention, this is something that's in line, that's really an approach very similar to what has been done in POD neural networks by Esteban and others. So same idea, like doing an offline fitting of coefficients and modes in the case. Okay, so
may I ask a question as well? This is Adar from Brown.
Yeah. Hi.
So you take from phi x to t, right? So you're basically doing the inference of the entire system on the latent space, right? After the PCA?
After the PCA, yes, that's correct.
Awesome. Okay, thanks.
Right. So if now assemble all these blocks, we have 4 blocks, right? 2, all the red is for displacement, 2 are the black ones are for the coefficients. So if we assemble these and we use the sort of projection layer, totally consistent with the DeepONet architecture, right? That's what we obtain. And these are the predictions. Okay, these are test predictions. So for unseen scenarios and like at unseen times. And like the reds, again, it's very indistinguishable, the predictions made by the what we call SVD DeepONet, okay, and the original integration of the OD. Okay? So now let's assume that instead we freeze these the blocks that we fitted using the SVD solution, right? But instead of using the same parameters that we fit before, that we obtained from the fit before, we actually retrain these just based on the input and like in this training architecture here, like for this training architecture here. Okay, so we freeze these 2 blocks, but we train these other 2. Okay, and this is something very consistent with a POD DeepONet proposed way before us by Lulu and like Crunch group. Okay, so we are really fixing the modes in a certain sense, but we are training for the coefficients. Okay. Now, if instead we don't freeze anything, but we train everything from the scratch in this architecture, that's what the vanilla DeepONet. Okay, that's the vanilla DeepONet that automatically finds the modes. So these outputs here of the trunk, in terms of the 2 red lines that you see for the trunk for the displacement, and 2 black lines here for the velocity. Okay. And that's the prediction that it is able to make. Okay, so there is, of course, like we don't have anymore the constraint on the orthogonality of the modes. Okay, but the nice thing is that the vanilla DeepONet training, okay, even if the architecture is exactly the same as the 2 that I showed before, is automatically to find this projection. Okay, and there are advantages, of course, in that, because we can use unstructured mesh, like unstructured data, so mesh-free data. We can use it fixed informed training, right? Multi-fidelity training, and that's exactly like the past months of Crunch group, right? What we are trying, like what we're claiming in this paper is that this is very useful also for autonomously discovering a better transformation, that I will show you in a bit what I mean with that. Okay. So, but like a side note is that this interpretation here, like this view here, is also useful for some ideas, I believe. In terms of mode interpretation and also modes use. Okay, so Lulu and again Crunch group in the fair comparison paper, they propose multiple architecture for the DeepONet, right? In terms of sharing trunk, sharing branches, and so on. So what I want to mention here is that if we use just one trunk for both the displacement and the velocity, okay, so we share the modes for these 2 states, right? That's equivalent to do something like that. So to create a snapshot matrix by concatenating the snapshot matrix for X and for V, and performing SVD on that. Okay, and again, these gives it like very good accuracy as well. So the important point is that this is possible, like the good accuracy in this case is possible because X and V had very similar modes, okay, in this case. So it needs to be like, we need to be careful when we use shared trunks, right? And the assumptions that we make in the type of modes that we expect from the different state variables. Okay, so now this is just a toy problem, again, for showing this SVD interpretation. I go to the real application, right? So this is a mechanism, a chemical mechanism, 0D. We have an isobaric 0D reactor. I will not spend too much time describing that, but the point is that we have 18 species, so it's kind of high dimensional, and temperature, so 19 total state variables. So we do the same idea. We sample, I believe, like 500 initial conditions in a very large range of initial conditions. So this is equivalent ratio. So like this governs the mass fractions of the relative mass fractions of the components in the mixture, and it's pretty wide range. And the temperature range, the initial temperature range is very wide, within 1,000 and 2,000 Kelvin. Okay, we use in time integration for creating these training scenarios, like 500 training scenarios. Okay, and we train a DeepONet. DeepONet that's very big. Okay, so there are 19 different DeepONets in a certain sense, each DeepONet for a different state, okay, and each composed by branch and the trunk. Okay? So if we look at, for example, at one branch and trunk for T, that's how they will look like. Okay? So there will be kind of deep neural network with a number of like 40 in this case, for example, 40 neurons inside each layer, and the last layer it's made by 20 neurons. Okay, so in the equivalence before, okay, in a certain sense it means like if we're using 20 output for this trunk, we're in a certain sense using 20 modes, okay, for representing the dynamics of this particular state variable T, temperature. Okay? These are the results that we obtain. There are some oscillations, like the accuracy is not really what we were expecting, because like the network is relatively big. We have a lot of parameters, and a very important point is that, again, we are trying to surrogate the dynamics. So we want to couple these surrogate with CFD in like for avoiding very expensive time integration. So it would be very nice to have a very cheap surrogate, so something very relatively small in terms of width, in terms of depth of the networks, right? So it's relatively expensive surrogate, but they're also notable inaccuracy. So we're trying to investigate why we have these inaccuracy here. Okay, and we went back to the interpretation that I showed you before. So we tried to construct, for example, for the hydrogen species, we tried to construct a snapshot matrix with the 500 scenarios that we construct. Right? We perform SVD, like PCA in this case, and that's what we find. So we find that we need 95, like in order to retrieve 95% of the cumulative energy content in this matrix here, we need sort of 15 for the singular values. In order to obtain 99, we need like 40, which is pretty big, right? So if we use only the first 20 modes, that's what we obtain, right? Which is very consistent with what we observed before when we were using 20 modes for the DeepONet, okay? Even more, another issue is that that's what we observe when we go to high, to the modes corresponding to very low singular values, okay? To modes that have very low energy content. They start to oscillate a lot. And so these are very hard to be fed by neural network, to be regressed by neural network, right? So, and we are trying to, like, we were wondering why, and then we came out, I think, with this idea. So if you look at the profiles, for example, for hydrogen, but all the other state variables look pretty much the same for a different scenario. So we have five different scenarios here. And they are pretty similar to each other, just translated in time. Translating in time, I mean, translating in the log scale, right? They are really scaled in a certain sense if you are in the linear scale. And so if we look at the metrics of the snapshot metrics from the top, in a certain sense, that's what we will see. We will see this translation here will have this effect. And we know that SVD is particularly inefficient in treating, in compressing data that's characterized by symmetries. And the symmetries, I mean, in general, shifts, stretches, and rotations. Okay. So, like, before going on, there's another side note. I think that the analysis of the data before actually training the DeepONet, in terms of SVD, in like really the composition, I think it's very useful for deciding what is the right P, so the right number of output for trunk and branch, and for deciding how much, like what is the specificity that we need for the neural networks. Like something like that, right, will bring us to use a very deep and wide neural network compared to something way simpler. Okay. So so what we like, this is the modification that we created for this purpose, right? For dealing with these symmetries and the problem. So we call this a flex DeepONet in the sense that adds additional flexibility to the already flexible DeepONet. So we add the pre-transformation block. Pre-transformation block in terms of another block that connects the initial condition, so the input of the branch, to the input of the trunk. Okay. So what it really does, it creates so it shifts the original time in the log scale. So, okay, so in terms of linear, really stretches it the original time, and it's just a fit for a neural net. Okay? It gives one output for each of the 19 states that we have. Okay, and that's what it does in terms, like, it really aligns the data. Like the red lines are the output of this block here. So the transform times, like that's plotted as function of the transform time. They really align the data so that they are way easier to be decomposed by the projection layer of the DeepONet. So this is very similar to the shifted POD, the idea that's been around for like 3-4 years. There is many work in the POD community on taking care of these shifts that happens in the dynamics. And we find out in the SIAM UQ conference that something similar has been proposed as well by the ETH group. In particular, this is a master thesis. That's pretty impressive master thesis for being thesis, in which they did something similar, like applying this shifting block to DeepONet. The difference here is that this is like a generic, it's not really just shifting, okay? So any symmetries in terms like rigid, but not only rigid, like any sort of symmetry that's contained in the dynamics in terms of rotation, translation, and stretches should really be kept in this way, should really be taken into account through a pre-transformation block. So I'll show you like later what I mean with that. And another modification that we made is adding another coefficient, so another output to the branch. So in combustion community, there is a lot of work going on in principal component analysis, starting from, I think, 2012, 2015, those years. There is a lot of literature about the importance of centering and scaling before performing PCA, in order to increase the accuracy, like the compressive power of PCA. So in general, what people do is really centering all the snapshots in the matrix as function of a coefficient based on a coefficient that's function of the initial conditions. That's function of that's really dependent on the column, and then scaling also in the same way, like a scenario dependent scale. Okay, so that's what we wanted to add here. That's what I think in part was missing in terms of like original vanilla DeepONet. So the scaling is already absorbed by B. So in a certain sense, DeepONet already learns this scaling. The centering, though, normally is done through a B and additional coefficients here, which is not function of the initial condition, just a scaling parameter. Okay, so in our opinion, like this can help the generalization capabilities. There is a work, very interesting work, came out last year in the centering and scaling influence for the topology of the manifold, which is like very well connected to this work. So these are the results. Again, 19 species, and you see like the different order of magnitudes that we have. So temperature ranges between 1,000 and 3,000, but also have ammonia mass fraction, for example, between like the order of 10 to the power minus 6. So like, of course, there are some inaccuracy here and there, but like it's pretty impressive also compared to other surrogation works in the field. Now, there is the issue though, which is given by the fact that, again, I was showing before, we cannot really limit our prediction to 19 species. We need something that goes above in terms of number of reactions, number of species, a number of states that we can treat in our surrogation. Okay. So the idea is then combining reduced order modeling to neural operator, in particular to DeepONet, for this particular application. And so one strategy that we adopted, that we presented last month at the International Conference on Numerical Combustion, is really an hybrid approach, in the sense that we reduce only some of the states, and we do that through PCA. Okay, so we keep, let's say, 4 states of the initial, for example, 50 that we have, and we reduce the remaining 46 through PCA. So we have a latent space composed by, let's say, 20 principal components and the 4 original states. Okay, and then we reconstruct the states that we compress to a nonlinear decoder. Okay, so these are two advantages. So the first advantage is that we work like the latent space is still a physical space in the sense that we have the same shapes, like we have the equations that govern the problem having the same shape. Okay, maybe different coefficients, but the form of the equation are the same as the original, the ones in the original space. And so for example, we can apply physics-informed losses. Okay, and the other advantage though is that the nonlinear decoder, of course, adds the reconstruction capabilities that the inverse PCA will not be able to achieve. Okay, so this is like the general framework. Okay, just a picture of the general framework. So the problem that we're investigating is a methane air gas mixture. So 53 state variables. So it's pretty big mixture. And we performed the compression to the latent space, as I showed you before in the slide before. And here we have then 24 DeepONets in a certain sense. Okay, so DeepONets composed by 24 branches and 24 trunks and 24 dot layers that predict the evolution of these latent variables. That then we reconstruct based on the hybrid reconstruction approach that I showed you before. And again, the initial conditions are, the range of initial conditions are the same as before. So very wide ranges, okay? And these are the predictions, which are pretty impressive. Of course, there are some inaccuracies. So the black lines here are the original, the ones from the ODE integration. The blue are the ones just purely, the dynamics purely compressed and decompressed through this hybrid PCA decoder approach. Okay? And the red are the prediction of the DeepONet. Okay? So you see that, like, other than some small accuracy, in general, we're really able to retrieve the dynamics in a very good way. So again, the ultimate goal, our ultimate goal is coupling with CFD simulations, right? So we want to expand to larger spaces of initial conditions and training to emulate general chemical evolution. And with that, I mean, like something similar to what Verticali's group has been doing in the 2021 paper. So the idea of really time marching in the dynamics with steps of DeepONets. Okay, so this is an example with the mass spring damper system that I was showing before. All the results that I'm showing right now are fully data-driven. So we're not using physics-informed yet. That's what we're working on right now. Okay, and also we want to consider uncertainty aware extensions of these DeepONets. It's been done in the past by Crunch Group as well. This is an example with undersampled data, so way less data than what I showed you before. In order to, this is done with MC dropout. We're also working on base back prop, but just the idea is really have a confidence interval around the predictions and deciding where we need more data, right? So, and of course, we want to explore mechanisms that have even more species, okay? So now this is the first part of the talk. Now in the second part of the talk, so the first part of the talk was really focused on showing that previous effort on SVD, PCA, and POD, like for example, shifted POD methodology can help DeepONet in particular extend the flexibility, interpretability, and so on. Now we try to show the opposite, that really DeepONet can help SVD approach, can extend even SVD, PCA, and POD approaches, okay? Yeah, so this is an example of what I mean. So it's a rigid body dynamics. So it's a rigid body that's really translating in space as a spiral, and it's rotating and it's also scaling. Okay, and we have 200 time snapshots that form this video in an XY grid made of 200 by 200 points. Okay, so a lot of symmetries, of course, like all the symmetries I was mentioning before that really SVD doesn't like, right? And indeed, when you go performing SVD on these, by the way, this is instead in POD approach, right? So what I mean is that the snapshots are really done for one time for each of the times in the XY. So this is X and Y, and this is T. Okay, if we do SVD on that, you see what we need. Like we need at least 150 singular values in order to retrieve 95% of the energy, the cumulative energy. And that's the consequence of SVD. Okay, so with 128, you see the resolution that we're able to achieve. So when we challenge the DeepONet even more, right? So this was done purely with SVD. Now we want to train DeepONet, and we challenge even more. So because we give it, instead of giving the nice points on the grid, we'd actually give completely random points in X, Y, but also in T. Okay, and way less points. So before we had 200 by 200, now we have 100 by 100. Yeah, this is probably wrong. And instead of sampling inside, maybe going back, instead of sampling in between -20 and 20, we just sample, sorry, -15 and 15, we just sample in a smaller window, okay, which is -10 and 10. And this is the DeepONet that we use. So we have 6 layers with 128 neurons each. And so like 128 modes, okay? And that's the predictions that we obtain with this vanilla DeepONet. So you see that, look at the predictions inside the training domain are not accurate, but even worse outside, of course. Okay, and this is because, again, the projection that's happening is really not capable, in a certain sense, of dealing in an efficient way with all the symmetries that are involved, okay, in the dynamics. So we did the same what we was doing before, but this time, instead of just considering the shifting net, we also have a stretch net and the rotation net. So 3 different neural network blocks that give in output some shifting coefficient, some stretching coefficient, and one angle for the rotation matrix. Okay. And we use just one mode. Before we were using 128 in the vanilla DeepONet. Now we use just one single mode. Okay. So that's the mode that we retrieve. Okay. Automatically from the data. And that's how it is performed compared to the vanilla DeepONet, right? Just because we, in a certain, like the pre-transformation network really does is finding out what is the reference frame, the moving reference frame. So the reference frame that moves within time by rotating, stretching, and shifting, right? That in which like the dynamics is really happening. Okay, so one mode, which represents the rigid by itself, is enough for describing everything. And this, of course, helps not only the interpretability, but also the generalization capabilities. So you see even outside the domain, of course, we know what's happening, right? And the nice part is that the vanilla DeepONet that I showed before had 165,000 parameters. Now we're able to do everything with 2,000. Okay, so it's way faster surrogate, other than being more predictive, right? So now the last example that I will present instead is on a different topic, certain different topic.
Hey, can I actually ask a question? First of all, that looks great, and I wanted to understand how the DeepONet actually structured or how it functions. So basically, you have prior knowledge, right? That your system is changing in rotations and in scale, right? And you're trying to learn some kind of an operator that knows this kind of rotation at scale, right? Mm-hmm. So what, for example, how do you define those branches of the rotation and the scale, like the signs that you showed previously? You just use many signs or something, or a single sign, or
use many? Sorry, many what?
So what goes in as training data? Let's see.
Oh, training data. Training data is just, in this case, is just really, let's say that I have 3 columns. The first column is the time of the time instant I'm selecting. Okay. The second 2 columns represent the value of x, y, right? So the location of the point that I'm choosing in time, and the output is just the z, is a 3rd dimension here, okay, which is like in a certain sense the color of the, like that here appears as a color. okay, which is like the rigid body. So there is another dimension here, right, which is a function of the space and time, right, which
Yes.
is represented as a color. So that's the output that I use, and I just use that for training the DeepONet. It's just training in the classic vanilla DeepONet way.
Yeah, I see. So how does S and theta come into the play?
Here, S and theta. So again, so like what really this automatically finds automatically in the sense that while training the DeepONet, okay, these blocks here find this particular coefficient, these 4 particular coefficients, right, that allow the transformation of the regional coordinates in terms of changing the reference frame, right?
Mm-hmm.
So shifting and stretching and rotating, right? And so what comes out from these is actually the position, but in the moving reference frame.
Ah, I see. Okay.
Right. So
I understand.
then if I do everything in the moving reference frame, then that's one single mode because it's rigid body.
Mm-hmm. Yeah. Okay, gotcha.
Yeah.
Cool. Thank you.
You're welcome. So yeah, so I was going to this other example. This is like slightly different, like slightly different topic. So what's going on here again? I was showing before this picture here, which is like pretty much what's going on in the shock layer, in the re-entry, in the atmospheric re-entry of capsules, at the re-entry or entering in general. Like this can be Earth atmosphere, can be Mars atmosphere. And I was saying that we really need the microscopic resolution. The resolution at the molecular and atomic level, okay? And what what Professor Pains's group does, and what I used to do like during my PhD, is really this approach here. So starting from what we call the first principle of quantum physics. So it's ab initio simulations, okay? Which means that we really simulate the molecules and the atoms interacting with each other in a quasi-classical way, which means that the equations are the Hamiltonian equations, okay, classical equations, but there is an interaction that's giving based on potential and surfaces that are from quantum chemistry. Okay, so that's a hybrid approach that allows the calculation of reaction rates, which are really, in a certain sense, the probabilities of a reaction happening based on how many times we measure the probability during the collisions. And then we use these reaction rate coefficients for solving a master equation, for studying the evolution of the number density of each of the states, combined with the Navier-Stokes equation. So we make predictions in the flow, and we can predict like quantum interest, like the heat flux, and so on, for design purposes, of course. Okay. This is the method that we use for what I showed before, for the quasi-classical trajectory calculation. So we select the translational temperature, okay, which defines a Boltzmann distribution, Max distribution in this case, that gives you like the energy content in the translation in the collision in a certain sense, okay. So then we sample an initial, so we select, actually not even sample, we select an initial state I, and we simulate tens of thousands of collisions between this state I and an atom. Okay, we see all the possible outcomes. So we can quantify the probability of a certain outcome, and these transform to cross sections and then rate coefficients. Okay, so we repeat these for all the states, but the real point is that what we obtain is this matrix here in a certain sense. So we have an initial state that has a certain probability, if you want, of ending in a final state J. And this matrix here contains these are 10 to the power 8 processes, okay, almost like so 100 million processes, okay. Not just that, we have to repeat this for multiple temperatures, so each of the coefficients at the end will be function of temperature, okay. So the real point is that in order to compute this matrix here, which like looks pretty simple in a certain sense to do, we need billions of trajectories, okay. So the computational cost is huge. And the question is, can we actually reduce this cost? For example, can we retrieve some sort of modes of these matrices here and use these just for predicting some missing columns or some columns that we don't want to compute, right? So there are complications though. So the first complication is that what I write here as state, like as index of the state, so I and J, are not really physical quantities, okay? Just convenience way for calling the state, but they don't represent much, this index here. So the actual state has properties that are multidimensional, that like that are really, we found like in our like many works of our previous group, we found that like they're really based on the diatomic potential properties. Like this, what you see here is a very fancy way for plotting the diatomic potential. So like in the chemistry class, this is normally just like a 2D function, no? Like a Morse potential, for example, as function of the distance, like the bond between the two atoms in the molecule. So here we have another component, which is is given by the fact that this molecule is rotating and there is the centrifugal effect that complicates everything. So, but my point is that if we actually see, okay, this matrix here in the original latent space, physical latent space, there are patterns that are sort of understandable. Okay, that makes sense. And here, what you see, for example, is 5 of the columns here, 5 of the 6,000 columns that are this matrix. Okay, in terms of these 5 clusters centered in the initial state. Okay, and these represent really the rate coefficients starting from a certain state I to end up in a certain state G, certain state J. Okay, so if we want to do, for example, SVD, we cannot really do that in this initial state space. Okay. The other point is that, again, we want to reduce the computational cost. So we don't have access to all the columns. We just have to very small amount of these columns. Like at the end, we have less than 1% of the original data. Okay, if we really want to save the computational cost. So how can we actually retrieve this sort of modes? Okay, so before leaving University of Illinois, I was like trying like I was starting this project here. That's now is that is brought on by Mitra Sharma and Ivan Zanardi, and that are PhDs there. And the idea is using DeepONet for really retrieving that. So this DeepONet is pretty simple. It's just one branch and one trunk. The input of the branch are really the initial state. So the columns of the matrix before, okay? But in terms of actually 4 quantities that are connected to the atomic potential, okay? And the input of the trunk instead are the differences in properties between the state I, okay? So the centering, if you want, of these clusters and a generic state J, okay? And these are, again, like difference in all the properties that we here. So the properties in I minus properties in J. These are the predictions that we obtain. For example, when we train just with 1% of the data for the O2 plus O process, so for the oxygen system. Okay, these are the results that we obtain from QCT, which are also very noisy, and this is what we retrieve with DeepONet. Okay, so again, 1% of the computational cost. These are the predictions that we are able to make forward propagating these rates in terms of state-to-state properties. Okay, in terms of like evolution of the distribution of these states, but also these are some integrated quantities, which is very important for then the CFD world, like for NASA, Air Force purposes. So in terms of relaxation time, all these dynamics. And the agreement is excellent. And even more interesting is that if we use a different system, so we trained, again, the DeepONet, for example, with the oxygen system, and we use it for making prediction about another system. Okay, we obtain some, at least for some temperature at the moment, this is fully work in progress, but the predictions that we're able to make are very consistent with the physics. Like this, again, like the black line, the black dots are the QCT, so the results from highly expensive simulations with billions of trajectories, and this is from the DeepONet train for another system. And this is the evolution of the mass fraction for this case here. You see, like the agreement is pretty interesting. So what we're trying to do now is really doing transfer learning. So this is not enough, like, but if we use even less states for the entry system, you know, for updating something that we already trained with the tree, of course, the agreement will be even better. So just in summary, just for concluding, so we investigated similarities and differences between DeepONet and SVD based methods. And so this interpretation here brought us to add some blocks in the original DeepONet architecture in order to characterize dynamics with symmetries. Okay? And we suggested also, in view of this analogy, we suggested applications outside the operator learning. So really, we believe that DeepONet has a lot of potential also for POD, PCA, even DMD application. And we should like also results for the efficient prediction of reaction rate coefficients. Okay, so there is no at least an explicit operator, but even the implicit operator is very integrated in the problem that I showed you before. Like it's Monte Carlo on billions of trajectories, right? So we then combined DeepONet and dimensionality reduction for the surrogation of combustion chemistry, and we saw that the surrogate that we obtain, even for chemical systems that have very high dimensionality, are very efficient and with small errors, and they are able to work with a very wide ranges of initial conditions. So with that, I concluded. If there are any questions.
Hi, I'm Vivek. I'm a PhD student at Brown. I have a question. Can you come to slide 27?
Yeah. Yeah, right.
Yes, yeah. It's regarding the prenet part. Yeah. Can you go a few slides behind so that can be seen?
This one.
Yes, so if I understand correctly, you define a prenet that decides the shift in the log scale or the scale in the usual scale of the time that is dependent on just the initial condition.
That's correct. Yes.
Can you tell me why you did this, like motivation behind doing this, why you felt this will help solving the oscillation problem, if I understand correctly?
Yeah, so I will go back 2 slides then. Yeah. So that's something like you see here in a certain. So again, these are for the same species. So for the same dynamical state, HU, these are 5 different scenarios. Okay, and you see that the dynamics is very similar. Yeah, it's just sort of translated in time. Yeah, for sure. It's also, I mean, stretched and shifting in Y, but in terms of X, right?
Yeah.
So when we stack all these, we concatenate all these scenarios, you will see something like this in a certain sense. If you are able, if you are smart enough to arrange them in an increasing way. Okay? Yeah. So this is the metrics that we, in a certain sense, implicitly apply a projection, like a decomposition to with DeepONet, right? Like if we do that in SVD, we do in an explicit way, but if we do with DeepONet, we do in a sort of more, you know.
Yes, it's learning the basis and the coefficients, correct?
Right. So it's well known, like Brunton and Kutz, for example. There is like there is an entire chapter like focus on these, like on the inefficiencies of symmetries for at the beginning for PCA, because SVD in general, but also for POD in like later in the chapter, right? And it explained very well. So these like it's not really like it's not smart enough in a certain sense as SVD to understand that these columns and these columns are pretty much the same, just stretched, right? So it will give you different modes for representing these columns, even if they're pretty much the same. Right. Okay. So what it does, this pre-transformation that I showed you before, it actually transforms this oblique line, you know, into an horizontal line, because it realigns all the data automatically, all the columns, right? And so it tells you at the point, of course, SVD is like, okay, this is the same mode.
Okay. Okay. Thank you. So you are forecasting just from the initial condition. You are predicting all the time steps.
This is for the initial condition, because each of the columns here is a different initial condition. It's a different scenario, right? Correct. So the realignment that you want to do is the function of the initial condition.
Sure, sure. Okay, thank you.
I had a question real quick. So if you go back to your slide the block diagram slide. I think it's a couple maybe after this one that describe the encoder architecture, and then
oh yes, this one.
There's a couple. Well, actually, so this has it. I think it's maybe the one after this, but yeah, there we go. Perfect. So you have to hear the input states. There's 53 of them. Some of them were not embedded. What was the selection criteria for not embedding some of them? Was that like a heuristic, or is there some sort of methodical approach to that?
Yes, so that's a very good point. So in this case, we just wanted to test the methodology in general. In reality, there might be some species that are very minor, right? In terms of presence in the actual mixture, but they're very important for pollution or for the actual dynamics. So you don't want to lose accuracy on that based on compressing and decompressing them. So you just want to keep them. So it's really application based. So you see what I mean?
Okay.
Like, yeah.
Yeah. So in this case, you have. I mean, did you actually pick these with temperature and nitrogen oxide?
Yes. For this particular case, yes. But we try different. Like it works in general. You see what I mean? Like for this particular case, it's actually it's more a generic approach for when we will have to go to higher space. Okay. So right now, like even with just using 25 principal components or projecting everything that without keeping, I mean, the accuracy is pretty okay. In general, like in the future, like for application which we want really to preserve accuracy for particular, this is, I think, a good way for doing that. Yeah.
Okay, got it. So it's problem dependent. So the only other question I had was on the right, you have the nonlinear decoder. How is that learned or trained?
Yeah, so we train all together, right? So this train offline, not with the DeepONet.
Oh, okay. So this is trained almost like an autoencoder. Yeah. Okay. Okay.
This is a feed for a neural network with, if I remember what it was, for layers. Sorry, for layers.
Yes. Okay. So it's embedded. Okay. So the encoder is the PCA and the decoder is. So are you not just learning the inverse of PCA when you do this?
If it was linear activation functions with just one layer, yes, or even with multiple layers. But in this case, no, right? Because
I see that. Yeah, that makes sense. Okay. Okay, cool. Yeah, no, great results. Great presentation. Thank you.
Thanks.
Do we have any more questions for our speaker?
Just one more question. Why did you choose to use nonlinear decoder? I didn't get that part instead of PCA itself. Or what is the choice? Why did you choose PCA as encoder or instead of a nonlinear encoder as well? What your choice criterion for encoder and decoder?
Yeah, so PCA is mainly for these, right? So because in the space that we project to is still physical, like it's a linear projection, right? So linear projection really we preserve the equations in a certain sense. The coefficients will be different, but the shape of the equations will be the same. So that's why the particular encoding. For the decoding part, like the results I showed you before, again, the dashed blue compared to the black is the compression reconstruction error, right? Yeah. If I do PCA here, so if I use something purely like the inverse of PCA, so something purely linear, the accuracy will be disaster, like we tried, and that's bad. So we will need way more principal components. So way more states in the latent space, in the DeepONet space, in order to achieve the same accuracy. Okay, so that's the trick. That's why the hybrid. Sorry. Or using as many states as low number of states as possible, but still preserving the equations. Okay.
Thank you.
Yeah. Any more questions? Okay, so if there's no more question, thank you, Sam, for your
presentation. For the invitation. Yeah.
Yeah. Before I close it, I want to apologize to our speakers on behalf of George for his absence in this week's seminar. He's currently on plan, so he cannot attend this meeting. He'll definitely catch up later by watching the recordings. We have recording every week. So, okay, sorry guys. And yeah, this is it for this week's quant seminar. Everyone has a good weekend. Yeah, see you.